Hello, this is Todd Booth, and I'll be covering Network Security Essentials, and we're into Chapter 9. Now, Chapter 9 is about IP security. So what we're thinking about is, can we secure data at the IP level and make it application independent? The reason for this is there are application-specific security mechanisms for a number of application areas, including electronic mail, which was SMIME PGP. We have client server, we learned about Kerbos, web access, we learned about secure sockets layer, and others. However, users have security concerns that are cut across all the protocol layers. For example, an enterprise can run a secure private IP network by disallowing links to untrusted sites, by encrypting packets that leave the premises, and by authenticating packets that enter the premise. By implementing security at the IP level, an organization can ensure secure networking not only for applications that have security mechanisms, but also for the many security ignorant applications which have no ability for security. Now, the IP level security encompasses three functional areas: authentication, confidentiality, and key management. The authentication mechanisms assures that a received packet was in fact transmitted by the party identified as the source in the packet header. In addition, this mechanism assures that the packet has not been altered in transit. The confidentiality facility enables communicating nodes to encrypt messages to prevent eavesdropping by third parties. The key management facility is concerned with the secure exchange of keys. Okay, and here's a quote for you. Go ahead and pause and read. And we'll begin this chapter with an overview of IP security, IPsec, and an introduction to the IPsec architecture. We then look at each of the three functional areas in detail. So here's the overview for IP security. In 1994, the Internet Architecture Board, IAB, issued a report titled Security in the Internet Architecture, RFC 1636. The report identified key areas for security mechanisms. Along these were the need to secure the network infrastructure from unauthorized monitoring and control of network traffic, and the need to secure end-user to end-user traffic using authentication and encryption mechanisms. To provide security, the IAB included authentication and encryption as necessary security features in the next generation IP, which has been issued as IP version 6. Fortunately, these security capabilities were designed to be usable both with the current IPv4 and the future IPv6. This means that vendors can begin offering these features now, and many vendors now do offer some IPsec capability in their products. The IPsec specification now exists as a set of Internet standards. So let's talk about the applications of IPsec. IPsec provides the capability to secure communications across a LAN, across private and public WANs, and across the Internet. Examples of its use include the following: secure branch office connectivity over the Internet. A company can build a secure virtual private network over the Internet or over a public WAN. This enables a business to rely heavily on the Internet and reduce its need for private networks, saving costs and network management overhead. Secure remote access over the Internet. An end user whose system is equipped with IP security protocols can make a local call to an Internet Service Provider, ISP, and gain secure access to a company network. This reduces the cost of toll charges for traveling employees and telecommuters. Establishing extranet and internet connectivity with partners. IPsec can be used to secure communication with other organizations, ensuring authentication and confidentiality by providing a key exchange mechanism. Enhancing electronic commerce security. Even though some web and electronic commerce applications have built-in security protocols, the use of IPsec enhances that security. IPsec guarantees that all traffic designated by the network administrator is both encrypted and authenticated using an additional layer of security to whatever is provided at the application layer. The principal feature of IPsec that enables it to support these varied applications is that it can encrypt and/or authenticate all traffic at the IP level. Thus, all distributed applications, including remote logon, client server, email, file transfer, web access, and so on, can be secured. Okay, this figure, an IP security scenario, is a typical scenario of IPsec usage. An organization maintains LANs at dispersed locations. Non-secure IP traffic is connected on each LAN. For traffic off-site through some sort of private or public WAN, IPsec protocols are used. These protocols operate in networking devices such as routers or firewalls that connect each LAN to the outside world. The IPsec networking device will typically encrypt and compress all traffic going into the WAN and decrypt and decompress traffic from the WAN. These operations are transparent to workstations and servers on the LAN. Secure transmission is also possible with individual users who dial into the WAN. Such user workstations must implement the IPsec protocols to provide security. And this is something I do. I mean, what I do when I'm at work in my office is I have a site-to-site VPN to different places, and I can access different equipment such as the InfoSec lab. And that allows me to use any equipment in my office. I have different PCs, and I can connect through the same site-to-site VPN, and then everything's encrypted, and there's also authentication involved. If I wanted to, I don't need to use a site-to-site VLAN. I can just run software on my PC, a VPN client like the Cisco VPN client, or I can run a native client off Windows, and then I can connect to the InfoSec lab. I enter in the correct credentials, and then I can log in. And the credentials can be user ID password, but they can also be certificate based. And then I can even send data across that connection, and I can pick and choose what's going to be encrypted and what's going to be not. And I can choose if I'm going to have a VPN and get a remote IP address from the remote side or not. Sometimes I need it, sometimes I don't. So what are the benefits of IPsec? Well, for the example I just gave you, it provides security. Without IPsec, I've got no encryption and I've got no authentication. So it's kind of like a wild, scary world. And then I have to rely on the application security. But this is really cool because I can just take Telnet, which is not secure, it's clear text, it's very dangerous, and I can put it over an SSH encrypted connection, or I can put it over an IPsec connection and have full security. So some of the benefits of IPsec are when IPsec is implemented in a firewall or a router, and what I use quite often is Cisco ASAs, adaptive security appliances, and you can also call it a VPN server. It provides strong security that can be applied to all traffic crossing the perimeter. Traffic within a company or work group does not incur the overhead of security-related processing. So the administrator and I can configure it and say what's going to be encrypted, what's not. Now, IPsec in a firewall is resistant to bypass if all traffic from the outside must use IP and the firewall is the only means of entrance from the internet to the organization. Now, IPsec is below the transport layer TCP UDP, and so it's transparent to applications. This is really awesome because it works with web traffic and email traffic and all kinds of different traffic. There is no need to change software on a user or server system when IPsec is implemented in the firewall or router. Even if IPsec is implemented in end systems, upper layer software, including applications, is not affected. So it's going to work for all your traffic. So you can be an internet cafe, you can use IPsec to connect to your home, and then from your home you can connect to the internet, and that way all the traffic across the internet cafe all the way to your home is going to be encrypted. So it's as if you're surfing from home from a security standpoint. Now, IPsec can be transparent to end users as well. There's no need to train users on security mechanisms, issuing keying materials on a per user basis, or revoking key materials when the when the user leaves the organization. So it has a bunch of advantages. Now, IPsec can provide security for individual users if needed. And this is useful for offsite workers and for setting up a secure virtual subnet within an organization for sensitive applications. And the way I would describe it is, from my office, I can use a VPN client software and connect to a VPN server at the InfoSec lab, and then I can get into and access all the equipment. I'm authenticated, everything's encrypted, we're good to go. But again, if I want to, I don't have to authenticate at the user level. I can just say anyone from my office, well, it's a site-to-site connection. If I have the site-to-site connection from my office to the InfoSec, I could say everyone in my office can access the InfoSec lab. So that's the other way to do it. So there's different modes, site-to-site and client-server. So let's talk about routing applications. In addition to supporting end users and protecting premises systems and networks, IPsec can play a vital role in the routing architecture required for internetworking. So here's a list of some examples of the use of IPsec. IPsec can assure that a router advertisement, a new router advertises its presence, comes from an authorized router. Otherwise, you might have these rogue routers jumping in and trying to mess up all the routing tables, and which is basically denial of service. Nothing will get anywhere. Or they may just try to implement a man-in-the-middle attack. Also, a neighbor advertisement, a router trying to establish or maintain a neighbor relationship, can verify the authenticity of the other router. So again, what we can do is implement security so that our routers can communicate intelligently with each other and have it authentic and encrypted. So we can also redirect messages from the router to which the initial IP packet was sent, so that we don't get IP spoofing attacks. A router update is not forged because we can implement security, and if we don't have these security measures, an opponent can disrupt communications or divert traffic. Routing protocols such as OSPF should run on top of security associations between routers that are defined by IPsec. And we can see a lot of things are pointing to IPsec documents. Now, IPsec encompasses three functional areas: authenticity, confidentiality, and key management. The totality of IPsec spec is scattered across dozens of RFCs and draft IETF documents, making this the most complex and difficult to grasp of all IETF specifications. Maybe that's why it's my favorite. I just love this IPsec and IKE, and I'm doing site-to-site VPNs and client-server VPNs all the time. The best way to grasp the concept of IPsec is to consult the latest version of the IPsec document roadmap, which as of this writing is RFC 6071, and Internet Key Exchange, IKE, document roadmap, February 2011. The documents can be categorized into the following groups. Architecture covers the general concepts, security requirements, definitions, and mechanisms defining IPsec technology. The current specification is RFC 4301, Security Architecture for the Internet Protocol. Now, one protocol is called Authentication Header, and it's an extension header to provide message authentication. And the current spec is RFC 4302, IP Authentication Header. Because message authentication is provided by ESP, the use of AH is deprecated. It is included in IPsec version 3 for backward compatibility, but should not be used in new applications. We do not discuss AH in this chapter. Encapsulating security payload, ESP, consists of an encapsulating header and trailer used to provide encryption or combined encryption authentication. The current spec is RFC 4303, IP Encapsulating Security Payload, ESP. We also have Internet Key Exchange, IKE, which is a collection of documents describing the key management schemes for use within IPsec. The main specification is RFC 5996, IKE version 2 protocol, and there are a number of related RFCs. We have cryptographic algorithms. This category encompasses a large set of documents that define and describe cryptographic algorithms for encryption. message authentication, pseudorandom functions, PRFs, and cryptographic key exchange. There are a variety of other IPsec related RFCs, including those dealing with security policy and management information base, MIB. Here are the IPsec services. IPsec provides security services at the IP layer by enabling a system to select required security protocols, determine the algorithms for use for the services, and put in place any cryptographic keys required to provide the requested services. Two protocols are used to provide security: an authentication protocol designated by the header of the protocol, authentication header, AH, and a combined encryption authentication protocol designated by the format of the packet for that protocol, encapsulating security payload, ESP. RFC 4301 lists the following services: access control, connectionless integrity, data origin authenticity, rejection of replayed packets, a form of partial sequence integrity, confidentiality encryption, limited traffic flow confidentiality. You need to understand transport and tunnel modes. Now both AH and ESP support two modes of use: transport and tunnel mode. The operation of these two modes is best understood in the context of a description of ESP, and here we have an overview. Transport mode provides protection primarily for upper layer protocols. That is, transport mode protection extends to the payload of the IP packet, and examples include a TCP or UDP segment or an ICMP packet, all of which operate directly above IP in a host protocol stack. Typically, transport mode is used for end-to-end communication between hosts, a client and a server, or two workstations. When a host runs AH or ESP over IP version 4, the payload is the data that normally follows the header. For IP version 6, the payload is the data that normally follows both the IP header and any IPv6 extension headers that are present, with the possible exception of the destination options header, which may be included in the protection. ESP in transport mode encrypts and optionally authenticates the IP payload, but not the IP header. AH in transport mode authenticates the IP payload and selected portions of the IP header. Now, tunnel mode provides protection to the entire IP packet. To achieve this, after the AH or ESP fields are added to the IP packet, the entire packet plus security fields is treated as the payload of the new outer IP packet with a new outer IP header. The entire original inner packet travels through a tunnel from one point of a network to another. No routers along the way are able to examine the inner IP header. Because the original packet is encapsulated, the new larger packet may have totally different source and destination addresses, adding to the security. Tunnel mode is used when one or both ends of a security association are a security gateway, such as a firewall or router that implements IPsec. With tunnel mode, a number of hosts on networks behind firewalls may engage in secure communications without implementing IPsec. And that's what I was referring to with a site-to-site VPN. With tunneling, on my PC, I don't have to do any encryption at all. I run normally, and then it's going to hit my local VPN server, and then it will tunnel all my traffic and encrypt everything to the other side. So it's kind of nice because I don't need to make any changes to my client OS or utilities or configuration. It just works. Now, the unprotected packets generated by such hosts are tunneled through external networks by tunnel mode SAs, which are security associations, which are set up by the IPsec software in the firewall or in the secure router at the boundary of the local network. ESP in tunnel mode encrypts and optionally authenticates the entire inner IP packet, including the inner IP header. AH in tunnel mode authenticates the entire inner IP packet and selected portions of the outer IP header. So here we have a table of tunnel mode and transport mode functionality. So just pause and check it out. And here's the IPsec architecture, and you can see how the process works exactly. We've got the IKE version 2 and the IPsec, and we've got packets going back and forth, and the IKE sets up a secure association so we can negotiate the IPsec security association. Now, fundamental to the operation of IPsec is the concept of a security policy applied to each IP packet that transits from a source to destination. An IPsec policy is determined primarily by the interaction of two databases, the Security Association Database and the Security Policy Database. And this section provides an overview of these two databases and then summarizes their use during the IPsec operation. And you can see the relevant relationships in this figure. So we'll talk about the Security Association, the SA now. A key concept that appears in both the authentication and confidentiality mechanisms for IP is the Security Association. An association is a one-way logical connection between a sender and a receiver that affords security services to the traffic carried on it. If a peer relationship is needed for two-way secure exchange, then two security associations required, one in each direction. A security association is uniquely identified by three parameters. The Security Parameters Index, SPI, a 32-bit unsigned integer assigned to this SA and having local significance only. The SPI is carried in the AH and ESP headers to enable the receiving system to select the SA under which a received packet will be processed. The IP destination address. This is the address of the destination endpoint of the SA, which may be an end user system or a network system such as a firewall, router, or VPN server. Security Protocol Identifier. This field from the outer IP header indicates whether the association is an AH or ESP security association. Hence, in any IP packet, the security association is uniquely identified by the destination address in the IP version 4 or IP version 6 header, and the SPI in the enclosed extension header, AH or ESP. Security Association Database, SAD. In each IPsec implementation, there is a nominal Security Association Database that defines the parameters associated with each SA. A security association is normally defined by the following parameters in an SAD entry. A security parameter index, which is a value selected by the receiving end of an SA to uniquely identify the SA. In an SAD entry for an outbound SA, the SPI is used to construct the packet's AH or ESP header. In an SAD entry for an inbound SA, the SPI is used to map traffic to the appropriate SA. A sequence number counter, a 32-bit value used to generate the sequence number field in an AH or ESP header, and that is required for all implementations of IPsec. There's a sequence counter overflow, a flag indicating whether overflow of the sequence number counter should generate an audible event and prevent further transmission of packets on this SA. That's also required for all implementations. An anti-replay window. That's used to determine whether an inbound AH or ESP packet is a replay. Also required for all implementations. An AH information, we have authentication algorithm keys, lifetimes, and related parameters used with AH. And if you're using AH, that would be required. Then on the other hand, instead of AH, we may use ESP. And ESP information includes encryption and authentication algorithms, keys, initialization values, keys, lifetimes, and related parameters being used with ESP. Then we have a lifetime of the security association, a time interval or byte count after which an SA must be replaced with a new SA and a new SPI or terminated. Plus it includes an indication of which of these actions should occur. Then we have the IPsec protocol mode. It needs to be tunnel, transport, or wildcard for negotiation. The path MTU. Any observed path maximum transmission unit, which is the maximum size of a packet that can be transmitted without fragmentation, and aging variables. The key management mechanism that is used to distribute keys is coupled to the authentication and privacy mechanisms only by way of the Security Parameters Index, SPI. Hence, authentication and privacy have been specified independent of any key management mechanism. IPsec provides the user with considerable flexibility in the way in which IPsec services are applied to IP traffic. As we will see later, SAs can be combined in a number of ways to yield the desired user configuration. Furthermore, IPsec provides a high degree of granularity in discriminating between traffic that is afforded IPsec protection and then traffic is allowed to bypass IPsec, in the former case relating IP traffic to SAs. And what this means is the following. If you're sending traffic between two different cities like Stockholm and Madrid, and it's the same company, they may have private networks on both sides, and they may wish to encrypt all traffic between those two private networks. However, on the other hand, perhaps some of the traffic between the two sites does not need to be encrypted, or perhaps it already is encrypted. Think about this. What if they had a backup which is 100 gig, and the backup is already encrypted? They may not wish to bother encrypting it again across the IPsec. That's a lot of data to encrypt twice. So they may choose for a certain IP address on the remote destination. For that, they're going to allow clear text to go through the tunnel. And for the rest of the traffic, they're going to do encryption. Okay, we have the Security Policy Database, the SPD, and the means by which IP traffic is related to specific SAs, or no SA if it doesn't match, is the Nominal Security Policy Database. In its simplest form, an SPD contains entries, one of which defines a subset of all IP traffic and points to an SA for that traffic. In more complex environments, there may be multiple entries that potentially relate to a single SA or multiple SAs associated with a single SPD entry. The reader is referred to relevant IPsec documents for a full discussion. And you can check out, for example, you can go to Wikipedia and get summaries of this information. I also recommend you go to perhaps Cisco or Juniper, and you can read their technical documentation. You can also go to the RFCs, which is a great place to go. And that's via the IETF.org. So each SPD entry is defined by a set of IP and upper layer protocol field values called selectors. In effect, these selectors are used to filter outgoing traffic in order to map it to a particular SA. Outbound processing obeys the following general sequence for IP packets. 1. Compare the values of the appropriate fields in the packet with the selector bits against the SPD to find a matching SPD entry, which will point to 0 or more SAs. Determine the SA, if any, for this packet and associated SPI, and then do the required IPsec processing, AH or ESP processing. Okay, here's the SPD entries, and you can see the following selectors determine an SPD entry. You can look through and read all these. And the following selectors determine an SPD entry: a remote IP address. This may be a single IP address, an enumerated list or range of IP addresses, or a wildcard mask of IP addresses. And the latter are required to support more than one destination system which share the same SA.
A local IP address. This may be a single IP address, a enumerated list or range of IP addresses, a wildcard mask. The latter two are required to support more than one source system sharing the same SA behind a firewall, for example. And then we have the next layer protocol. The IP protocol header, IP4 or 6 or 6 extension, includes a field which is protocol for IPv4 or next header for IP version 6. It could even be an IPv extension, v6, that designates the protocol operating over IP. This is an individual protocol number, or maybe any, or for IPv6 only. Opaque. If AH or ESP is used, then this IP protocol header immediately precedes the AH or ESP header in the packet. It also needs a name, a user identifier from the operating system. This is not a field in the IP or upper layer headers, but is available if IPsec is running on the same operating system as the user. Local and remote ports. These may be individual TCP or UDP port values, or a list or a wildcard port. Okay, and here I thought it'd be fun just to pull up a configuration from Cisco. I'm doing VPN configuration, site to site, and client to server, and I'm doing a lot lately because I'm creating some labs. So here's what it looks like, and here's what you need to do. You got a pure IP address, so you might have a site in Stockholm and in Madrid. So let's say we're at the Stockholm VPN server. What we can do is type in the peer address of Madrid. I'm just going to make up an address, and we can say the connection name is the same, or we could name it something else. Then the interface, and if I'm going to protect traffic that's going across the internet in the Cisco terminology, my outside interface is the one that connects to the internet. So that's what I would normally choose. If you wanted to protect the traffic within Stockholm, not across the internet, but within Stockholm, for example, from the PC client to the VPN server on the local side, you would use the inside interface. And then I say what networks I want to protect. And by protect, what I mean is what network traffic do I want to encrypt and make confidential. So perhaps on the Stockholm side, we'll have a private address of 123 class C, and then the remote network, perhaps I'm going to connect to in Madrid. They might have a whole bunch of private networks, but perhaps they have a network called 127. And I'll do class C. I'm going to block all the traffic using a wildcard mask, so I don't have to type in every single host on both sides. I could have a list of different IP addresses or different masks, etc. So I have a lot of control over this. And then for the IPsec enabling, I have to choose a group policy or configure a group policy. Let's go ahead and manage those so you can see what it looks like. So I'm going to just add a new one, and I give it a name called Demo1. And then I can inherit all these default configurations which are used perhaps for a lot of different sites, but I think it's more fun to create each one individually for you. So I'm going to take away the default, and then I'm going to configure this. Now, if in Madrid they're using IKE version 2, I would click just here. If they're just using version 1, I would click just there. But there's a trick people don't always understand. Sometimes it's not always the best thing to configure exactly perfect between the two matching servers. So for example, I might click version 1 and version 2 and configure both. That way, if Madrid changes from a VPN that's running version 1 to 2, I don't have to do any reconfiguration on my side. For now, I'll just leave version 2. Then what we can do is say what we're going to filter, and we can manage, and we can say what traffic we're going to match here. And there's a whole bunch of rules that I can use. That's the matching traffic. Now here's, we can have an idle timeout. We talked about that, how long it's going to be before it times out and needs to create a new association. Anyway, sooner or later we say okay. We're going to choose that demo, and then we're going to go back in here, and you can see demos filled in. And here's the two fields from the group policy selected above. I have enabled both. Here, if I want to configure the IKE version 1 settings, I do it here. version 2 settings, I do it here. And look at this. For version 1, it starts out with ESP AES 128 SHA and then continues on to negotiate everything else. It's going to start with the other side trying to negotiate for this first setting. Now maybe I don't want AES 128. Maybe I want like 256. So what I can do is I can take this settings here with the 256 MD5, although I'd normally choose SHA, and I'll put that at the front, and then I'll paste it in, and there we go. Now it's going to attempt first to negotiate and use it with AES 256 MD5. You can use a pre-shared key, and that's an awesome way for testing. You can get going really quick. But in the real world, after you're doing testing, you want to roll it out. What you should do is use device certificates. So you can go ahead and manage your certificates. You can add a new certificate, and you can import it from a file, or there's different ways. You can have a decryption password because maybe it's got a lock on it. So you can also click down here to add a new certificate, and look here, you can generate a self-signed certificates. And like I said before, those are great and they're super for testing, but when users connect to you, if you have a self-signed certificate, they're going to normally get a warning message unless you mess with their certificate store within the client system. So there you go. That's adding a certificate. That's IK version 1. You jump over to version 2, and look at this. You've got a local key and a remote key. So you can have different keys that you put on both sides here. You still have choices for your IKE policy. And IKE policy, what we do is we use IKE, create a security association, and then within that association we have an encrypted session, and that encrypted session is where we negotiate IPsec settings for this IPsec security association. So here you have the confidentiality settings for encryption and integrity checking on the IKE, and then once that's done, it's going to negotiate IPsec, and this is the way I like it. AES 256. I normally just use that. Oh boy, and that's IKE version 2. So we're all done with that. And then if you can, there's a NAT exempt, and if you're doing NAT traffic because you have private addresses on both sides, you normally want to exempt that traffic when you're going site to site between two private networks. Then we even have advanced settings here. Okay. It's going to want some information, so I will give it to it. Here's let's just take away IKE1. We don't have to configure it now. Voila. We put in some pre-shared key, and then we go into advanced. Now here we have perfect forward secrecy. We talked about this perfect forward secrecy in the book, and you can enable it or disable it on your site to site. Let's say we enable it. Look at that. We've got the Diffie-Hellman group. We need to choose what group, and we have different groups, 1, 2, 5, 14, etc. And here's, look, the Security Association lifetime, just what the book's talking about. And this is where you entered in the Cisco router. And we have some more information. And we have even ESP version 3 on the Cisco device if we wish to configure that. Okay, well, that's the end of that part. And we're back. Okay, so here we have a table, the host SPD example, and you can see various parameters, which makes it a little bit easier to understand what's going on here. So this table, it provides an example of an SPD on a host system as opposed to a network system such as a VPN server. This table reflects the following configuration. A local network configuration consists of two networks. The basic corporate network has the IP network number 1230. The local configuration also includes a secure LAN, often known as a DMZ, that is identified by 1240. The DMZ is protected from both the outside world and the rest of the corporate LAN by firewalls. This is defense in depth. The host in this example has the IP address 12310 and it is authorized to connect to the server 12410 in the DMZ. And the entries in the SPD should be self-explanatory. If not, you probably need a little more background in TCP/IP networking. For example, UDP port 500 is the designated port for IKE. Any traffic from the local host to remote host for purposes of an IKE exchange bypasses the IPsec processing. We have another flowchart, and this figure highlights the main elements of IPsec processing for outbound traffic. A block of data from a higher layer such as TCP is passed down to the IP layer, and an IP packet is formed consisting of an IP header and an IP body. Then the following steps occur. 1. IPsec searches the SPD for a match to this packet. 2. If no match is found, then the packet is discarded and an error message is generated. If a match is found, further processing is determined by the first matching entry in the SPD. If the policy for this packet is discard, then the packet is discarded. If the policy is bypass, then there is no further IPsec processing. The packet is forwarded to the network for transmission. If the policy is protect, then there's a search in the SAD for a matching entry. If no entry is found, then a IK is involved to create an SA with the appropriate keys, and an entry is made in the SA. Then the matching entry in the SAD determines the processing for this packet. Either encryption, authentication, or both can be performed, and either transport or tunnel mode can be used. The packet is then forwarded to the network for transmission. So here's a flowchart, and in this figure it highlights the main elements of IPsec processing for inbound traffic. An incoming IP packet triggers the IPsec processing. So go ahead and pause and read through that. So in this figure, it shows the top level format of an ESP packet. It contains the following fields: a security parameters index, which identifies a security association, a sequence number, and this is increased counter, and this provides an anti-replay function, as discussed before for AH. Payload data, this is a transport level segment for transport mode, or it's an IP packet for tunnel mode that is protected by encryption. Then we have some padding, and then we have the length of the padding, and then we have the next header. And that identifies the type of data contained in the payload data field by identifying the first header in that payload. For example, extension header in IP version 6, or an upper layer protocol such as TCP in IPv4. And then we have an integrity check, which is a variable length field, and it contains the integrity check value computed over the ESP packet. And then when any combined mode algorithm is employed, the algorithm itself is expected to return both decrypted plain text and a pass-fail indication for the integrity check. For combined mode algorithms, the ICV that would normally appear at the end of the ESP packet when integrity is selected may be omitted. When the ICV is omitted and the integrity is selected, it's the responsibility of the combined mode algorithm to encode within the payload data an ICV equivalent means of verification of the integrity of the packet. Now, two additional fields may be present in the payload. An initialization value, IV, or nonce, is present if this is required by the encryption or authentication encryption algorithm, which is used by ESP. Now, if tunnel mode is being used, then the IPsec implementation may add traffic flow confidentiality, TFC, padding after the payload data and before the padding field. Encapsulating security payload, ESP. Now, the payload data, padding, pad length, and next header fields are encrypted by the ESP service. If the algorithm used to encrypt the payload requires cryptographic synchronization data, such as an initialization vector IV, then this data may be carried explicitly at the beginning of the payload data field. If included, an IV is usually not encrypted, although it is often referred to as being part of the ciphertext. The ICV field is optional. It is present only if the integrity service is selected and is provided by either a separate integrity algorithm or a combined mode algorithm that uses an ICV. An ICV is computed after the encryption is performed. This order of processing facilitates rapid detection and rejection of replayed or bogus packets by the receiver prior to decrypting the packet, hence potentially reducing the impact of a denial of service attack. It also allows for the possibility of parallel processing of packets at the receiver, that is, decryption can take place in parallel with integrity checking. Note that because the ICV is not protected by encryption, a keyed integrity algorithm must be employed to compute the ICV. And the padding field serves several purposes. If an encryption algorithm requires the plain text to be a multiple of some number of bytes, for example, of a single block or blocks for a block cipher, the padding field is used to expand the plain text consisting of the payload data, padding, pad length, and next header fields to the required length. And also the ESP format requires the pad length and next header fields to be right aligned within a 32-bit word. Equivalently, the ciphertext must be an integer multiple of 32 bits. So the padding field meets this requirement. And there actually may be additional padding to provide partial traffic flow confidentiality by concealing the actual length of the payload. And here we have an anti-replay mechanism figure. Now, a replay attack is one in which an attacker obtains a copy of an authenticated packet and later transmits it to the intended destination. The receipt of duplicate authenticated IP packets may disrupt service in some way or have some other undesired consequence. It's the sequence number field that's designed to thwart such attacks. First, we discuss sequence number generation by the sender, and then we look at how it's processed by the recipient. So it's when an SA is established, the sender initializes a sequence number counter to 0, and each time a packet is sent, it's incremented. Thus, the first number to be used is 1, and if anti-replay is enabled, which is the default, the sender must not allow the sequence number to cycle past some value 2 to the 32nd minus 1, and then it just wraps around back to 0. Otherwise, there'd be multiple valid packets with the same sequence number. If the limit of 2 to the 32 minus 1 is reached, the sender should terminate the SA and negotiate a new SA with a new key. Because IP is connectionless and unreliable, the protocol does not guarantee that packets will be delivered in order and does not guarantee that all packets will be delivered. Therefore, the IPsec authentication document dictates that the receiver should implement a window of size W with a default of 64. And the right edge of the window represents the highest sequence number N for a valid packet. For any packet with a sequence number in the range from N minus W plus 1 to N that has been correctly received, i.e. properly authenticated, the corresponding slot in the window is marked. Inbound processing proceeds as follows when a packet is received. If the received packet falls within the window and is new, the MAC is checked. If the packet is authenticated, the corresponding slot in the window is marked. If the received packet is to the right of the window and is new, the MAC is checked. If the packet is authenticated, the window is advanced so that this new sequence number is to the right edge of the window and the corresponding slot in the window is marked. If the received packet is to the left of the window, or if an authentication fails, the packet is discarded. And this is an auditable event, which you can usually find in the log files. Okay, now we have a figure, and it's transport mode versus tunnel mode encryption. And the figure shows two ways in which the IPsec ESP service can be used. In the upper part of the diagram, encryption and optionally authentication is provided directly between two hosts. The figure shows how tunnel mode operation can be used to set up a virtual private network. In this example, an organization has 4 private networks interconnected across the internet. Hosts on the internet networks use the internet for transport of data, but do not interact with the other internet-based hosts. By terminating the tunnels at the security gateway to each internal network, the configuration allows the host to avoid implementing the security capability. The former technique is supported by a transport mode SA, while the latter technique uses a tunnel mode SA. In this section, we look at the scope of ESP for the two modes. The considerations are somewhat different for IP version 4 and version 6. We use the packet formats as a starting point. So here we have a figure, and it's the scope of ESP encryption and authentication. Transport mode ESP is used to encrypt and optionally authenticate the data carried by IP, for example, a TCP segment, as shown in the figure. For this mode, using IP version 4, the ESP header is inserted into the IP packet immediately prior to the transport layer header, TCP, UDP, ICMP, and an ESP trailer, which includes padding, pad length, next field header, is placed after the IP packet. If authentication is selected, the ESP authentication data field is added after the ESP trailer. The entire transport level segment plus the ESP trailer are encrypted. Authentication covers all of the ciphertext plus the ESP header. In the context of IP version 6, ESP is viewed as an end-to-end payload. That is, it is not examined or processed by intermediate routers. Therefore, the ESP header appears after the IP version 6 base header and the hop-by-hop routing fragment headers. The destination option extension header could appear before or after the ESP header, depending on the semantics desired. For IP version 6, encryption covers the entire transport level segment, plus the ESP trailer, plus the destination options extension header if it occurs after the ESP header. Again, authentication covers the ciphertext plus the ESP header. So here we have a figure, protocol operation for ESP, and this figure shows the protocol architecture for the two modes. So go ahead and pause and read through that. Combining security associations. Now, an individual SA can implement either the AH or ESP protocol, but not both. Sometimes a particular traffic flow will call for the services provided by both AH and ESP. Further, a particular traffic flow may require IPsec services between hosts, and for the same flow, separate services between the security gateways, such as a firewall. In all of these cases, multiple SAs must be employed for the same traffic flow to achieve the desired IPsec services. The term security association bundle refers to a sequence of SAs through which traffic must be processed to provide a desired set of IPsec services. The SAs in a bundle may terminate at different endpoints or at the same endpoints. Security associations may be combined into bundles in two ways. Transport adjacency refers to applying more than one security protocol to the same IP packet without invoking tunneling. This approach to combining AH and ESP allows for only one level of combination. Further nesting yields no added benefit since the processing is performed at one IPsec instance, the ultimate destination. Iterated tunneling refers to the application of multiple layers of security protocols effected through IP tunneling. This approach allows for multiple levels of nesting, since each tunnel can originate or terminate at a different IPsec site along the path. The two approaches can be combined, for example, having a separate SA between hosts travel part of the way through the tunnel, and then using a different SA between the security gateways. One interesting issue that arises when considering SA bundles is the order in which the authentication and encryption may be applied between a given pair of endpoints, and the different ways to do so. ESP with authentication option. Encryption and authentication can be combined in order to transmit an IP packet that has both confidentiality and authentication between hosts. We will look at several approaches. One approach is where the user first applies ESP to the data to be protected and then appends the authentication data field. And there's actually two subcases. Transport mode ESP, authentication and encryption applied to the IP payload delivered to the host, but the IP header is not protected. In tunnel mode ESP, authentication applies to the entire IP packet delivered to the outer IP destination address, for example a firewall, and authentication is performed at that destination. The entire inner IP packet is protected by the privacy mechanism for delivery to the inner IP destination. For both cases, authentication applies to the ciphertext rather than the plaintext. Transport adjacency. Another way to apply authentication after encryption is to use two bundled transport SAs, with the inner being an ESP SA and the outer being an AH SA. In this case, ESP is used without its authentication option. Because the inner SA is a transport SA, encryption is applied to the IP payload. The resulting packet consists of an IP header and possibly IPv6 header extension, followed by an ESP. AH is then applied in transport mode so that the authentication covers the ESP plus the original IP header and extensions, except for mutable fields, which are the ones that are changeable. The advantage of this approach over simply using a single ESP SA with the ESP authentication option is that the authentication covers more fields, including the source and destination IP addresses. The disadvantage is the overhead of two SAs versus one SA. Transport tunnel bundle. The use of authentication prior to encryption might be preferable for several reasons. First, because the authentication data are protected by encryption, it is impossible for anyone to intercept the message and alter the authentication data without detection. Second, it may be desirable to store the authentication information with the message at the destination for later reference. It is more convenient to do this if the authentication information applies to the unencrypted message. Otherwise, the message would have to be re-encrypted to verify the authentication information. One approach to applying authentication before encryption between two hosts is to use a bundle consisting of an inner H transport SA and an outer ESP tunnel SA. In this case, authentication is applied to the IP payload plus the IP header and extensions, except for the changeable mutable fields. The resulting IP packet is then processed in tunnel mode by ESP. The result is that the entire authenticated inner packet is encrypted and a new outer IP header extension is added. So here we have a figure, basic communications of security associations. The IPsec architecture document lists 4 examples of combinations of SAs that must be supported by compliant IPsec hosts. For example, workstations or servers or gateways. And these are illustrated in this figure. The lower part of each case in the figure represents the physical connectivity of the elements. The upper part represents the logical connectivity via one or more nested SAs. Each SA can be either AH or ESP. For host-to-host essays, the mode may be either transport or tunnel. Otherwise, it must be tunnel mode. Internet key exchange. The key management portion of IPsec involves the determination and distribution of secret keys. A typical requirement is 4 keys for communication between 2 applications. Transmit and receive pairs for both integrity and confidentiality. The IPsec architecture document mandates support for 2 types of key management. Manual. A system administrator manually configures each system with its own keys and with the keys of the other communication system. This is practical for very small static environments. Automated. An automated system enables the on-demand creation of keys for essays and facilitates the use of keys in a large distributed system with an evolving configuration. ISA-KMP Oakley. The default automated key management protocol for IPsec is referred to ISA-KMP Oakley and consists of the following elements. Oakley Key Determination Protocol. Oakley is a key exchange protocol based on the Diffie-Hellman algorithm, but providing added security. Oakley is generic in that it does not dictate the specific formats. Internet Security Association and Key Management Protocol, ISA-KMP. ISA-KMP provides a framework for Internet key management and provides the specific protocol support, including formats for negotiation of security attributes. ISA-KMP by itself does not dictate a specific key exchange algorithm. Rather, ISA-KMP consists of a set of message types that enable the use of a variety of key exchange algorithms. Oakley is the specific key exchange algorithm mandated for use within the initial version of ISA-KMP. In IKE version 2, the terms Oakley and ISA-KMP are no longer used, and there are significant differences from the use of Oakley and ISA-KMP in IKE version 1. Nevertheless, the basic functionality is the same. Features of IKE key determination. The IKE key determination algorithm is characterized by 5 important features. It employs a mechanism known as cookies to thwart clogging attacks. It enables the 2 parties to negotiate a group. This, in essence, specifies the global parameters of the Diffie-Hellman key exchange. It uses nonces to ensure against replay attacks. It enables the exchange of Diffie-Hellman public key values. It authenticates the Diffie-Hellman exchange to thwart man-in-the-middle attacks. Okay, the IKE version 2 protocol involves the exchange of messages in pairs. The first 2 pairs of exchanges are referred to as the initial exchanges. In the first exchange, the 2 peers exchange information concerning cryptographic algorithms and other security parameters they are willing to use, along with nonces and Diffie-Hellman values. The result of this exchange is to set up a special essay called the IKE SA. This essay defines parameters for a secure channel between the peers over which subsequent message exchanges take place. Thus, all subsequent IKE message exchanges are protected by encryption and message authentication. In the second exchange, the 2 parties authenticate one another and set up a first IPsec SA to be placed in the SADB and used for protecting ordinary, i.e. non-IKE communications between the peers. Thus, 4 messages are needed to establish the first SA for general use. The create child essay exchange can be used to establish further essays for protecting traffic. The informational exchange is used to exchange management information, IKE version 2 error messages, and other notifications. Here we have a figure on IKE formats. The figure shows the header format for an IKE message. It consists of the following field. Initiator SPI, a value chosen by the initiator to identify a unique IKE security association, SA. Responder SPI, a value chosen by the responder to identify a unique IKE SA. Next payload indicates the type of the first payload in the message. Payloads are discussed later. Major version, minor version, these indicate what version of IKE in use. Exchange type indicates the type of exchange, and they're discussed later. Flags indicate specific options set for this IKE exchange. 3 bits are defined so far. The initiator bit indicates whether this packet is sent by the SA initiator. The version bit indicates whether the transmitter is capable of using a higher major version number than the one currently indicated. The response bit indicates whether this is a response to a message containing the same message ID. There's also a message ID, and that's used to control retransmission of lost packets and matching of requests and responses. There's a length field, the length of total messages, including header plus all payloads. All IKE payloads begin with the same generic payload header. The next payload field has a value of 0 if this is the last payload in the message. Otherwise, its value is the type of the next payload. The payload length field indicates the length in octets of this payload, including the generic payload header. The critical bit is 0 if the sender wants the recipient to skip this payload if it does not understand the payload type code in the next payload field of the previous message. It is set to 1 if the sender wants the recipient to reject this entire message if it does not understand the payload type. Here's a table with IKE payload types. The table summarizes the payload types defined for IKE and lists the fields or parameters that are part of each payload. The SA payload is used to begin the establishment of an SA. The payload has a complex hierarchical structure. The payload may contain multiple proposals. Each proposal may contain multiple protocols. Each protocol may contain multiple transforms, and each transform may contain multiple attributes. These elements are formatted as substructures within the payload as follows. Proposal. This structure includes a proposal number, a protocol ID, which could be AH, ESP, or IKE, an indicator of the number of transforms, and then a transform substructure. If more than one protocol is to be included in a proposal, then there is a subsequent proposal substructure with the same proposal number. Transform. Different protocols support different transform types. The transforms are used primarily to define cryptographic algorithms to be used with a particular protocol. Attribute. Each transform may include attributes that modify or complete the specification of the transform. An example is key length. The key exchange payload can be used for a variety of key exchange techniques, including Oakley, Diffie-Hellman, and the RSA-based key exchange used by PGP. The key exchange data field contains the data required to generate a session key and is dependent on the key exchange algorithm used. The identification payload is used to determine the identity of communicating peers and may be used for determining authenticity of information. Typically, the ID data field will contain an IP version 4 or IP version 6 address. The certificate payload transfers a public key certificate. The certificate encoding field indicates the type of certificate or certificate-related information, which may include the following: PKCS number 7 wrapped X.509 certificate, PGP certificate, DNS signed key, X.509 certificate, signature. X.509 certificate, key exchange. Kerberos tokens, certificate revocation list, CRL. Authority revocation list, ARL. SPKI certificate. At any point in an IKE exchange, the sender may include a certificate request payload to request the certificate of the other communicating entity. The payload may list more than one certificate type that is acceptable and more than one certificate authority that is acceptable. The authentication payload contains data used for message authentication purposes. The authentication method types so far defined are RSA digital signature, shared key message integrity code, and DSS digital signature. The nonce payload contains random data used to guarantee liveness during an exchange and to protect against replay attacks. And here we have a couple of tables. The IPsec version 3 and IKE version 3 protocols rely on a variety of types of cryptographic algorithms. As we have seen in the book, there are many cryptographic algorithms of each type, each with a variety of parameters, such as key size. To promote interoperability, two RFCs define recommended suites of cryptographic algorithms and parameters for various applications. RFC 4308 defines two cryptographic suites for establishing virtual private networks. Suite VPN-A matches the commonly used corporate VPN security used in older IKE v1 implementations at the time of its issuance, which was in 2005 with IKE version 2. Suite VPN-B provides stronger security and is recommended for new VPNs that implement IPsec version 3 and IKE version 2. And the table A lists the algorithms and parameters for the two suites. There are several points to note about these two suites. Note that for symmetric cryptography, we have VPN-A relies on SSS and HMAC, while VPN-B relies exclusively on AES. Three types of secret key algorithms are used. Encryption. For encryption, the cipher block chain is used, that mode, CBC. We have message authentication. For message authentication, VPN-A relies on HMAC with SHA-1 with the output truncated to 96 bits. VPN-B relies on a variant of CMAC with the output truncated to 96 bits again. Pseudorandom function. IKE version 2 generates pseudorandom bits by repeated use of the MAC used for the message authentication. RFC 6379 defines four optional cryptographic suites that are compatible with United States NSA Suite B specifications. In 2005, the NSA issued Suite B, which defined the algorithms and strengths needed to protect both sensitive but unclassified and classified information for use in its cryptographic modernization program. The four suites defined in RFC 4869 provide choices for ESP and IKE. The four suites are differentiated by the choice of cryptographic algorithm strengths and a choice of whether ESP is to provide both confidentiality and integrity or integrity only. All of the suites offer greater protection than the two VPN suites defined in RFC 4308. And then the table 9.4b lists the algorithms and parameters for the two suites. As with RFC 4308, three categories of secret key algorithms are used. Encryption. For ESP, authenticated encryption is provided using the GCM mode with either 128-bit or 256-bit AES keys. For IKE encryption, CBC is used as it was for the VPN suites. Message authentication. For ESP, if only authentication is required, then GMAC is used. As discussed GMAC is simply the authentication portion of GMC. For IKE, message authentication is provided using HMAC with one of the SHA-3 hash algorithms. Pseudorandom function. As with the VPN suites, IKE version 2 in these suites generates pseudorandom bits by repeated use of the MAC used for message authentication. For the Diffie-Hellman algorithm, the use of elliptic curve groups module a prime is specified. For authentication, elliptic curve digital signatures are listed. The original IKE version 2 documents used RSA-based digital signatures. Equivalent or greater strength can be achieved using ECC with fewer key bits. And a summary. I'll just go over the main points. We've talked about IP security and given an overview. We've talked about IP security policy, including its security associations. We've talked about cryptographic suites, the encapsulating security payload, ESP. We also talked about AH, which is a bit older. And then we talked about combining security associations. And we talked about the Internet Key Exchange, which is the key exchange which is done before the IPsec security association is created. Okay, hope you enjoyed. Thanks for listening. Bye for now.